Speaking with us today, and she is the Gendell Assistant Professor of Engineering Systems and Public Policy at the Nicholas School of the Environment at Duke University. Her research focuses on public policy design for energy systems, with a particular emphasis on managing the risks arising from the uncertainties influencing the outcomes of government actions. Much of her current work focuses on the policies that affect capital investment decisions within the electricity industry and the corresponding costs to society of electricity and air emissions levels. Her models explore the effects of different government policies by representing the industry's decisions under uncertainty on future technological advancements, fuel prices, and emissions regulations. Dr. Patino-Echeverri received her PhD from the Department of Engineering and Public Policy at Carnegie Mellon University. And before she joined Duke University, she was a postdoc there at the Climate Decision Making Center at Carnegie Mellon. And so with that, I'd like to, and I should just point out, you all can see we have some upcoming energy policy seminars, the next one being Burson Unell, who's been working on New York state policy on the energy transition, and hopefully can give some translations and insights for New Jersey, and Rebecca Bohm, who looks at food consumption and greenhouse gas emissions and energy use in that process, and Jacqueline Berger, who will be speaking about energy efficiency and evaluation. But for now, I will turn it over to Dalia and welcome this presentation. If you have clarifications, you can type them in the chat or raise your hand, and then we'll try to hold questions until the end.
Thank you so much, Rachel, for the invitation. As I was saying, it's really nice to be connected with people outside of these four walls. Thank you, Kevin, for coordinating. And it's great to see all of you here. I will share my screen and tell you, for now, you just will see. Okay. And then let me just flip the presenter side, and should be able to see my slides now. Is that fine, Kevin? Yes, thank you. And if you have any clarification questions, please feel free to ask. That probably will help. I want to talk today about work we have been doing in my lab on the mechanisms by which we can reduce electric power sector emissions, greenhouse gas emissions, particularly using solar photovoltaic, energy efficiency, and battery energy storage. And I'm just going to start by saying something that everyone here knows, and is that in the middle of so much uncertainty, we know one thing, and that is that in order to reduce the chances of an increase of 1.5 centigrades in global mean temperatures, the emissions of CO2 must be only half of what they are today before 2030, and they must become zero by 2055. And if we are risk averse, then better if those emissions become zero by 2040. And that is a monumental challenge because just last year's global emissions exceeded 33 gigatons. So doing this is really a challenge everywhere, and especially in countries with very high emissions, where their economies depend a lot on the burning of fossil fuels, such as the United States, which despite great advancements replacing coal with natural gas due to the declining in natural gas prices shown here in this upper graph, still has the very large CO2 emissions, even when compared with other giants like China and India, and definitely very much when compared to the world. So how to limit global warming to 1.5 centigrades? Well, there are several pathways that differ in the details of how much of each energy source we need to use. Most of the pathways examined by the IPCC include carbon capture and sequestration and nuclear energy. But there is an agreement that we need really to achieve very fast and bold transitions in energy, in land use, in buildings, in transportation, and in industry. In energy, we need renewables for electricity to account for 60% of the mix. And we need to reduce energy demand by between 5 and 15%. We also need to keep land with more forest and less pasture. And we need to electrify buildings, transportation, and industry, and improve energy efficiency over there. Achieving this 60% of mix energy, 60% of the mix of electricity from renewables is hard in the US. Here is a chart of the progress made going away from coal, some of that replaced with natural gas. But still, despite all this significant change, fossil fuels still represent more than 60% of the US electricity mix. And then if we talk about other sources that are carbon-free, like nuclear, well, half of the nuclear power plants that we have in the United States are 30 years old. The other half are at least 20 years old. Then we can talk about hydro, for example, and what we know is that there is no great potential for new hydropower. In the best case, and this is calculated by the Hydrovision report, most recent one, in the best case, we can grow hydro by 50%, which means that it would go from representing 7% of the mix to represent 10% of the mix. So then the question is, how do we grow this wedge, particularly with wind and solar? How can we grow it to 50% or more in a decade? So the purpose of this presentation is to present results from research that we have conducted in my lab regarding pathways to decarbonization in an important part in the Southwest, which is the Duke Energy Progress, Duke Energy Carolinas system. I want to discuss the effects that extant power plants and potential new sources of energy and storage would have on air emissions, on the cost of electricity, and on reliability. Here is a map of this area. This is the Duke Energy Carolinas, Duke Energy Progress service territory. It is the largest vertically integrated utility in the United States. And it is part of Duke Energy, which is one of the largest energy holding companies in the country. Now, this area is special. In 2019, the CO2 emissions from this balancing authority were 634 pounds per megawatt hour. And that is lower than the average emissions in the United States. That's in fact 33% lower than what emissions are in the rest of the country. And also very interestingly, North Carolina ranks second in the United States by installed capacity of photovoltaics, second after California. And 10% of the solar PV generation in 2018 in the US, like using the IGRI data, was generated in this area. So if you take, so it's a place where PV can grow a lot. So if we are thinking about decarbonization, then we may consider this area a place where things may be easier, not easy, but easier or less challenging than in other places. So we're going to be asking a number of research questions, and that's what we have been trying to address in recent work. The first one is, how much rooftop photovoltaic can be integrated in today's DEC, Duke Energy Carolinas, DEP, Duke Energy Progress system? This is, part of this is in a paper that we published in, with my student, Bandar Al-Katani, and my former master student, Kira Moore. We're gonna be asking also how much is there, how much we can integrate if there is also aggressive investment in residential energy efficiency. And this is also work with former PhD student, Bandar Al-Katani. And because we will find that residential energy efficiency and rooftop PV are not enough to achieve deep decarbonization. We're going to be looking at utility scale PV and battery energy storage, asking what's the best way to pair the two. And that's work that is coming on applied energy from my PhD student, Edgar Virgües, and Chinese visiting scholar, Xianxun Wang. And finally, I'm just going to say a few words, and we can talk more about that later, on new work we're doing on how to schedule and dispatch electric generators to reduce the cost of renewables integration and maintain reliability in this region. And this is work funded by RPI, the RPI Perform program. Our project is called A Grid that is risk aware for clean electricity. And I'll tell you more, and it involves Ohio State University, Professor Antonio Conejo, North Carolina State University, Jordan Kern, and PNNL, a group they are led by Veronica de Tola. Okay, so I think everyone here knows that growing the share of wind and solar is very difficult for many reasons. For one, because wind and solar resources are remote and land intensive. The best solar and wind resources are far from the main centers. Their power output is variable and is not coincident with load. And it fluctuates significantly on short and long time scales. And this variation does not coincide with load patterns for the most part. And also, in addition of being variable, solar going from producing 0 at night to producing a lot at noon, it's also uncertain. We can never forecast what the production will be for either solar or wind without some error in the forecast. So it is very hard to cope with this variability and uncertainty if our conventional resources in the fleet, in the power generation fleet, are not flexible. And that's another reason why studying the North Carolina, South Carolina area is interesting. It's because more than half of the generation in this system, the CDEP, comes from nuclear plants. The nuclear plants represent 25% of the electricity installed capacity, generation installed capacity, and generate 49%. That is for 2015, and that's the plan for 2029 looks very much the same. The plants have at least a decade of continued permits to operate, and they are planning to apply for relicensing. Now, I also said there is significant solar. So the region has more than 1,000 megawatts of installed solar generation capacity. And as I said, it represented 10% this generation of the PV generation in the country. Okay, so how do we look at these research questions? Our method for the several studies that I am going to present always consists of simulating the hourly operations of the system. In the last study that I am not presenting results, I'm just describing on how to improve operations, we look at every 5 minutes operations. But for these other ones, we're just looking at hourly. And we account for all the technical constraints of the generators. That includes their minimum and maximum capacity to generate electricity, the downtimes that they have to as minimums, the ramping capability. And we also account for the startup emissions, not just average emissions, but making sure that we take into account that when power plants are shut down and need to start up, their emissions and fuel consumption to reach a stable level of generation are higher. And for the first study, we look at 8 scenarios that vary by the fleet. So we look at the 2015 or the 2025 fleet. We look at 6 nuclear, all the power plants in this system, which is nuclear plants, coal plants, hydropower, which includes 2 that are pumped hydro, natural gas combustion turbines, and natural gas combined cycle power plants. And we look at energy generation units, electricity generation units. So each plant has several. So we have several, like more than 200 electricity generation units represented. We look at the scenarios that consider different levels of flexibility for the nuclear plant. In the first study, we just look at two, which is one where the nuclear plant operates as a baseload plant. Sometimes it goes down for maintenance, but for the most part, it generates electricity, and on average for the whole year is an 87% of the capacity factor. And then another scenario that we consider to be the flexible nuclear plant, which is allowing it to ramp down to 70% of its natural of its installed capacity. And we also look at different fuel prices. So our model starts with a PV power generation module that simulates the electricity produced from rooftop arrays based on solar irradiance data, also based on household data, and based on solar penetration level. This model uses GIS ArcMap to merge 10 kilometer by 10 kilometer data set on global horizontal irradiance, or GHG, which is data in watts per square meter. And we merge that with a GIS shapefile that contains household census data, which is really the number of homes that are per square meter in North Carolina and South Carolina. The model assumes that 100% all of the households units in the region have the roof surface to accommodate a 4 kilowatt PV system. So this is like a small PV system that would be made of 16 3-foot by 5-foot PV modules, each of them rated at 250 watts. And we estimate the values of direct irradiance hitting the tilted module surface for each grid cell and for each hour of the year, of course, based on the global horizontal irradiance and the position of the sun relative to the tilted module. So using the equation of time. And we also look at, well, later we will just aggregate the power production from all the cells to get hourly PV generation for the entire system. And we subtract that from demand. So later I'll say what we have about demand, but we have a characterization of the housing units in North Carolina and South Carolina. And we have some energy efficiency scenarios. So we have our baseline of demand estimates. And from that, we can calculate net demand. So net demand is really just demand subtracting the generation from the rooftop solars. That's demand that the utility doesn't see. So the net demand is just what is seen by the utility. And we, in the model, we also have all the generator parameters for all the fleet, and all the assumptions we have made about the way the Duke Energy Progress, Duke Energy Carolinas operates. So what are the spinning reserves that they have? What are the penalties that they have if they have overgeneration or undergenerations? It's really representing what are the actions that they take when they have these problems. Etc. And then we put all of these into a day-ahead unit commitment model, which is a mixed integer linear program that gives us the hourly generator commitment schedule. And later we enter what we think is the actual net demand, not the estimate, what we had put before for as an input to the unit commitment, but the realized actual net demand. And we enter that into a real-time economic dispatch model. And we get from there what is the hourly generator dispatch schedule, what are the daily operating costs, the hourly generator statistics, and we can calculate system costs and CO2 emissions. So with this model, the first observation, looking at our household census data and the performance of our the assumptions about the performance of the PV systems installed and the demand of the whole system, what we find is that if 7% of the households in this region had the small 4 kilowatt rooftop PV systems, then these would generate 1% of the electricity in the area. Now, if instead of 7%, we had all the households with these small solar system, rooftop solar systems, then they would supply 16% of the electricity. This is, or 16% of penetration of PV electricity. So this is probably like the maximum we could do with our assumption of all rooftops, all households having the rooftop to accommodate 4 kilowatts. This is what we would achieve. Now, we run our simulation for every hour of the whole year. And then we find some interesting results. For example, the first one is that in the absence of storage and in the absence of assumptions about flexibility of the nuclear plants, the nuclear generation really imposes a limit on the penetration of rooftop solar because rooftop solar enters as a demand. So if we have here a graph of the time, and then here is gigawatt hours. If this line, horizontal line, is the electricity provided by nuclear plants when they are operating at 87% capacity, and this curve is the net demand, which is, as I said, the demand minus the rooftop PV generation, then the most we can have is 5.3% of penetration coming from rooftops. If we had more, then the demand would be lower than the supply from nuclear plants. And as we know, the fundamental goal of electricity power system operators is to maintain electricity supply equal to electricity demand at all times. So to accomplish this, there has to be a limit on the penetration of rooftop PV because it reduces load. So if it exceeds 5.2%, then there will be an imbalance between demand and supply, right? These lower lines of demand right here would be lower than the generation of the nuclear plants, and the nuclear plants, the supply would be higher than the demand. So this can be seen in another diagram. So we calculate for the 8 scenarios I described originally, how many hours do we have supply exceeding demand? And so for starters, we have the reference scenario, and we look at what would happen if we don't have any additional rooftop. We have only 5.3% or 9%. And what we see is that if we have 9% of electricity coming from rooftops, we will have 122 instances in a year when supply is more than demand. If it is only 5.3%, then this is manageable. And then this is the case, I mean, having a lot of times when supply exceeds demand is the case for every single scenario where we have 9% of penetration of electricity from rooftop solar. But this is if we assume that the nuclear power plants are inflexible. If the nuclear power plants are assumed to be flexible and they can ramp down to 70% of their capacity, then in our reference fleet, we would have only 4 instances of overgeneration. And on the fleet of 2025, we would have almost no instances. So we could achieve this penetration of 9%. This could be handled. Now, what is interesting is, in any case, CO2 emissions would be lowered under every scenario where you have inflexible nukes or flexible nukes. Or inflexible nukes would have some reliability issues and cost of dealing with these overgeneration events. But in any single case, these red lines, which is the percentage reductions in CO2 emissions, are significant. For example, what we can see is that there is between 10 and 13% less CO2 emitted under a 5.3 penetration of rooftop than under the baseline. So the baseline is 0, and we can see. And then if we had 9%, then the penetration it would be a lot higher. But having 5.3% penetration of rooftop requires having more than a third of the households in the region installing 4 kilowatt PV systems in their rooftops. Now, we can also assume that we will have a 9% rooftop penetration or penetration of electricity from rooftop generation, and that would result in higher CO2 emissions, between 16 and 20%, less CO2 emissions than in the baseline. But achieving this penetration of 9% would require more than half of the households to have these small 4 kilowatt PV rooftop installations. So then we ask, okay, what if we pair these rooftop electricity PV installations with energy efficiency? What if all homes are energy efficient? So we use the same modeling framework, but this time we assume also different scenarios of residential energy efficiency. We also assume that all nuclear plants can ramp down to between 70 and to 70% of their installed capacity. So this is the flexible nuclear scenario. And we estimate the residential electricity consumption of the HVAC systems, the lighting equipment, the refrigerator, freezer, dishwasher, range, clothes washer, dryer. We do this, so we use their parameters and we estimate their electricity consumption for each hour of the 365 days period that we are simulating. We do this for a typical household in 10 different climate zones in the DEC DEP service territory. And then for the HVAC, we have for the HVAC system, for our estimation of the electricity use, we have to calculate the heat transfer gain that is through the house envelope due to the differences between outdoor and indoor temperatures, and the solar heat gains through the windows and glasses, and the heat gains from air ventilation, and internal heat gains generated by people, lights, and appliances. And so we have also the assumptions about the building envelope with assumptions about house dimensions and window to wall ratios based on typical figures in North Carolina for each of the 10 climate zones. So we look at two scenarios. For the baseline, the building envelope has, we assume that 10% of the existing homes comply with the EPA Energy Star standards. And we assume that the other 90% in the base, under the baseline, are in compliance with the North Carolina Energy Conservation Code of 1996 and the South Carolina State Energy Code of 1986 as well. And then we have we look at several scenarios, but I'm just going to talk about the most stringent one, which is the Energy Star scenario, where we assume that all existing homes are fully retrofitted to comply with the Energy Star program. So it assumes retrofits to the building envelope, to the HVAC system, the lighting equipment, and all the major appliances. And we have the time series of electricity consumption from each of the typical households are later aggregated after being multiplied by a weighting factor representing the share of housing units in each climate zone. And the resulting hourly estimate of load, then we just scale it up to match the load in 2015 or 2025. Residential load accounts for about a third of the total annual load in the DEC DEP network. So if we account for, if we look at the energy study scenario, which is, as I said, the most stringent one, one that would only be possible in the absence of market and adoption barriers and policy barriers, then what we see is that if we have this scenario, then first of all, between 9 and 10% of the electricity generation would no longer be necessary. The range in this estimate is because we have uncertainty regarding whether most residential units today comply with the 1996 building codes or the 1978 building codes. We find that yet, although this is very good for reductions in electricity generation, the reduction in the daily peak load imposes a limit on the maximum share of electricity that can be generated from rooftop solar PV. For this case, it's 6.4%. So, and this is because the demand would be lower than the supply at certain times when PV production is high and the nukes cannot ramp down or shut down. And now, and this will happen unless we consider energy storage. If this level of energy efficiency, which is everything retrofitted to Energy Star standards, is paired with the maximum we can accommodate to have optimized cost, which is 6.4% of rooftop solar, then the cost of operating the system are going to be reduced. They are going to be 9% lower than what they would be. And CO2 emissions would be 25% lower. So we can have all homes retrofitted with Energy Star and add 6.4%, add rooftop solar, so that which is about 40% of the households having rooftop solar. That gives us 6.4% of rooftop PV electricity penetration, and we will accomplish 25% of CO2 emissions reductions and also reduce costs. Because we reduce costs, because we are also displacing, reducing the need to regenerate electricity, but also reducing the use of fossil fuels. But this is not enough, right? So we have to look at utility scale. So we see that rooftop PV plus end use would reduce about 26% of the CO2 emissions. So we need to consider utility scale PV, and we need to consider battery energy storage to achieve further reductions. And that's the question we ask next is, what is the best combination of PV and BES, battery energy storage? So the same method, we simulate hourly operations of the 221 electricity units that operated now. We looked at the fleet of 2016. And we look at 144 different fleets or scenarios. So we have a baseline fleet for 2016 that includes less than 2% of solar PV. And then we have this baseline paired with 6 gigawatts of PV, which would accomplish 5% of PV penetration. Then, or with 10% PV penetration, 15 or 20 or 25, which is an impressive 30 gigawatts of solar PV installed. And then we look at other scenarios that have the same baseline fleet of nuclear, hydro, coal, natural gas, the little solar or the solar that we have, and these additional PV that we're going to be installing, 5 levels of it. And we also add battery energy storage. We add different combinations. So we add batteries that are or 2 hours, 4 hours, or 6 hours of duration, and with different power and power capacities. So they can be either 1.8 or 2.5 times, like the megawatt hours in this battery energy storage would be between 1.8 and 2.5 times the megawatt capacity of the PV installed. So for the PV, we assume crystalline silicon vertical axis tracking systems with 95% inverter efficiencies and 14% system losses. And this would cost about $1 million per megawatt, including some transmission, balancing of costs, etc., land, leases, etc. For the batteries, we assume lithium-ion batteries with a 90% charge and discharge efficiency, which results in a 90% round-trip efficiency. And we assume that the cost for the 2-hour ones are around $400. The 4-hour duration batteries are $350, and the 6-hour duration batteries are $300. So we simulate these. So these ones are 135 scenarios, and with these others, this is the total of 144 scenarios. So we simulate a whole year of operations for each of these 144 scenarios. And we compare the CO2 emissions reductions we can get and the cost of abatement. So how much does it cost in dollars per ton of CO2 for each of them? So here, like each of these points is one configuration of the PV size and the type of battery, the size and the duration of the battery. And so, for example, and these stars are the ones that are the lowest among their family. So the first family is the family of configurations that have 6 gigawatts or 6,000 megawatts of photovoltaics. So the lowest, the one that achieves the lowest cost of abatement is one that also has 754 megawatts of a 2-hour duration battery energy storage. And the other one here, up here, is the one that corresponds to an installation of 30 gigawatts of PV and 5 gigawatts of batteries with 6 hours of duration. What we can see is that for the first, the cost of abatement is about $30. And for the second one, and we can achieve 17% of CO2 emissions reductions. And for the second one, for the last one, we can achieve a reduction of 57%, and the cost will be around $80 per ton of CO2. Now, because it comes at a cost, installing this PV and these batteries, and these capital costs are not offset by the savings in fuel, the levelized cost of electricity, so the dollars we pay for each megawatt hour of electricity in this system, are going to be more expensive, 8% more expensive than in the baseline, the system we have today. Now, in the case of having 30 gigawatts of PV and 5 gigawatts of battery, then the levelized cost of electricity is going to increase by 65%. So this is going to be higher than the baseline. Now, is 8% or 65% a lot? How much is needed to reduce, how much would we need to reduce the capital cost of these technologies, batteries and PV, so that we can, the capital costs are going to be offset by the savings in the fuel, in fuel consumption? Well, for the case when we have just 6 gigawatts of PV, which is 5% penetration of the whole mix, we would need a 50% reduction in PV costs to have no increases in the levelized cost of electricity. That means if PV capital costs come to down 50%, then we can install all these PV and these batteries, and it will not cost anything. The savings from not having to burn fossil fuels will offset the cost of this investment. In the other case, we would need an 84% reduction in PV costs to achieve a break-even point between the capital cost of this gigantic 30 gigawatt PV investment and 5 gigawatts of BES. The question is, are reductions of 50% or 84% in capital cost feasible or possible? And the answer is, we need to remember that since 1980, the capital costs of solar have been coming down by 10% each year. That in fact, since 1980 to today, the reduction has been of 99%. So that means that in about 5 years, it would be the capital cost of these smaller investments of PV would be paid for with just the reductions in system operational costs. And in about 9 years, we could have these 57% penetration of PV plus batteries at no cost. So the last thing I said I wanted to mention is that we can do all these investments, but we also need to improve the approaches we use to schedule and to dispatch generators to reduce the cost of renewables and the cost of integrating them. We need to account for the uncertainty on wind and solar and preposition all these generators accordingly. So currently we schedule generators planning for expected values of wind and solar production and knowing that there is an average forecast error, that we are always wrong. But instead of doing that, we need to consider a large number of detailed possible scenarios and schedule plans to minimize a function of the average cost and their variability. And we are just working on this for this system. We have done it for PJM, and we found that it was promising. We found that if you had integrated 12% of the electricity coming from wind, and you change the way the system is scheduled and dispatched, you would reduce emissions by 3.5% more, and you would reduce costs. So with the same fleet, you can reduce emissions and costs if the systems we use to schedule and dispatch power plants are better. So that's what we are trying to do in our ARPA-E funded project, which I hope to be able to tell you more about in a few months and years. And that's it. Thank you so much for your attention. I am very happy now to take any questions.
Have any considerations been given to the cost of infrastructure upgrades with the PV penetration?
I say that again, sorry.
Have your model given consideration to infrastructure upgrades required for PV penetration?
So in our model, we considered the cost of other infrastructure, so the transmission lines, the balance of plant, etc. We haven't looked at more than that. So like this is, so it is using ballpark estimates of what transmission would be needed for the different sizes, but we haven't, which is more work that needs to be done, looking exactly at where these plants will be located and what upgrades in the transmission and distribution system need to be made to ensure reliability.
Thank you.
This is Frank.
Hi, Frank. It's nice to meet you.
Same here. Thank you. Actually, maybe I'll turn on my video. For your presentation, you opted for a simulation approach, right? You optimized the hourly, and then for other work, the 5-minute, and then you did these simulations, which was nice because you could kind of build each assumption as it layered in. But it's kind of curious if, why did you pick that route versus more of a global optimization, expansion optimization framework?
So in the, you're talking about the last one, the battery study?
Well, no, everything up to that, where you had your hourly model, unit commitment hourly model, you put in solar, you put in energy efficiency, you put in, and you kind of built up the pieces, and then you simulated different nuclear flexibility, for example, and whole different cost structures. So another approach could have been just a generation expansion approach, right? You could have put in a model, all the different options, and then it would have told you, well, it's worth having, just X, Y, and Z. And I was just wondering, what was your thought in terms of making that approach?
It's a great question. Yes, so in the capacity, we've tried capacity expansion planning models in my group for other places. For example, we did one for Saudi Arabia, trying to interconnect the non-interconnected regions. And so over there, you are letting the model choose what would be with a goal you have in mind, right? So I have this goal of achieving these reductions or those reductions. We have done that as well. Here we were looking more at policy scenarios. So for example, when we picked the 25% penetration of PV from utility scale, and we said, well, that's twice what we have in the REPS of North Carolina. So we were looking at chunks. It makes the model more manageable, because the capacity expansion planning would also need to consider this, right? So there would be another layer above these simulations saying, let's try this level of electricity, this level of PV, this level of energy efficiency, this level of batteries, see if that meets the reliability constraints, see what are the costs, see what are, and then let's try another one. So it will probably try longer or more combinations of resources than what we are trying. It would be better because, as you saw, when I just looked at 5 different sizes of PV, so 5 gigawatts, 10 gigawatts, 15 up to 30 gigawatts. So this approach that you are suggesting, capacity planning, would give me would consider one that is in between that I never considered. But completing that would have been more computationally extensive than what we could handle at that time. That's something that we are, so although in the RPI project, we are not necessarily looking at capacity expansion planning, we're going to be considering future expansion, and we may need to do something like that. And that's where we are ramping up all our capability to probably take that approach. So yeah, it's the more sophisticated, nicer approach that we were not to do it at this level of detail, we had to do it this way.
Yeah, I guess I wasn't suggesting it's better, it's just different. I mean, it hides the expansion that would hide, because here, not just partly for presentation level, you can just see each piece, and then you can kind of interpolate visually, yeah, if you did a mixture of policies. But anyway, I was just kind of wondering.
Yeah, but and you are right that gives, so we couldn't explore, so you saw, actually, let me just show these graph of the batteries, or well, maybe I can, but we were seeing that with some level of PV, you can no longer reduce the cost, you have to add batteries, but then we jump at the level of PV that is 5 gigawatts larger. So yeah, we may be missing a sweet spot that will be good in between. We try to approximate it with these numbers, but yeah, we should move there at some point. Thank you.
I have a question.
Yes.
Theoretically, is the optimal ratio between the electricity produced by PV and the electricity produced by other sources that are not influenced by weather, is the optimal ratio or maximum ratio?
It's a good question. We would like to think that what we know is there is an optimal ratio of PV and batteries, right? So and there is also an optimal duration of batteries. So for the levels of PV that are not so much, like in the 5 gigawatts, like 5% of the system or 10% of the system electricity, short duration batteries are enough to compensate. If you are going to go to 30 gigawatts, which is 80% of the installed capacity of the system and 25% of its electricity, then you need batteries of very long duration. Now, for conventionals, if the conventional ones are flexible, then that wouldn't be any problem. But if you had just nuclear or a lot of nuclear like we have, you need anyways, we're assuming they can ramp down to 70% and they can shut down if you know you will not need it for some time. But still, with that, things become harder. Is there what we want to think is that no, we can decarbonize and we can have a lot of renewables and everything else be batteries or carbon free. Is there a sweet spot? I don't know. What we are showing is that yeah, you can get up to 25%, and it will be expensive, but within what we have been expecting, in a few years it will not be that expensive. It will be it will pay for itself. You know, the reductions in operations costs will cover the capital costs.
So my question is that to reach the goal to reduce the GHG reduction emission and also keep the continuous supply of the electricity, you take these two goals into consideration. So what is the possible have optimal or maximum ratio between these the different sources, the different electricity electricity produced by the different sources.
But if you're talking, I mean, in theory, we can have 100% renewables with storage, right? So that it's just that what is the cost? So we'll have to think if we have a goal for the cost, like not increasing levelized cost of electricity more than X, or not paying more than $150 per dollar of ton of CO2 per ton of CO2 abated, then there will be a ratio there, right? Like you could say, if you want to never pay more than $100 or $150 per every ton of CO2 you reduce, then yeah, you cannot have more than maybe what we had here, so 25% renewables. So what I am showing you is with 25% renewables, with 25% solar PV from utility scale, you get a high levelized cost of electricity, and you pay a lot for those CO2 emissions reductions.
Thank you.
But your question, yes, one will have to look. Give me one number, an anchor of how much do you want to spend, and I tell you what is the optimal ratio.
Yeah, thank you. Yeah.
We have a question from the chat. Someone was wondering what the residential electricity costs are in North Carolina.
It's about 10 cents per kilowatt hour. I think it's within the average of the US, maybe a little bit lower. Much lower than in New Jersey for sure, and New York, yes. This is a system with, as I said, 50% of the electricity coming from nuclears that have been already paid for, has been retiring coal, some natural gas, and a lot of natural gas units, solar, and hydro. Did I say hydro? Hydro representing about 2%, but a lot of hydro and pumps hydro. Yes.
Hi, Dr.
Yes.
Patino. I have a question. So have you considered, given that there's distributed energy resource, PVs are distributed energy resources, the architecture kind of, and the study changing from centralized to decentralized, maybe more regional microgrid type of solutions for reliability, and maybe there's a cost benefit for that. What are your thoughts about going from a centralized model to a decentralized model with more local, flexible assets?
Yes, we haven't, in our group, we haven't looked in detail at that aspect of the transition in North Carolina. That's something that is gonna be examined more carefully in the new project, where we are looking at the risk that is posed by different assets in the grid at different levels, and the need for the system operators to better characterize the uncertainty on those resources and plan ahead, right? So when Duke Energy owns a solar farm, it knows how it is maintained and what is its historical production, and can plan ahead for issues that may arise with this power plant, and also it has an idea of how this correlates with the demand. The production of this solar farm that they own and operate correlates with the demand. When a lot of the solar comes from behind the meter installations or with microgrids, etc., they will need, if this is a small portion of the system, it's okay, they can handle it. But if it is to become a large share, then there has to be a mechanism to better understand how these resources work, and for better plan for their variability and their uncertainty, and also for better compensate them, both because they may reduce the risk of the system, so like there used to be no risk related to fuel delivery in North Carolina. But so when the system operator was planning how to dispatch the power plants, they could assume, if I don't have enough, I just use more natural gas. Now they are very constrained about natural gas. So having these distributed resources is hedge against that, right? And has reliability benefits. So compensating for them would be good, but also accounting for the added risk would be necessary.
And just a follow-up question, because of your point about compensation, has kind of a carbon tax or some type of an emission compensation been considered in your study, and what are the impacts of that for that region?
Sorry, can you say again?
Compensation for maybe carbon reduction, carbon emission, or emission reduction generally. Has that been considered instead of just the capital cost being reduced?
Yes. So Duke Energy has a very ambitious goal. In the recent IRP, they reiterated their commitment to becoming net zero by 2050 and reducing emissions. I forgot now. Oh, I should know this, but very aggressive commitments. So among those, they are exploring a lot of alternatives, and some of them are, investments that are better done at the other side, just making those investments to achieve their climate goals. So the compensation, I don't know that they have gotten to that point, but really like very good financing and streamlining the processes of, for example, installing rooftop in customers' homes to get to that level of net zero emissions.
Great, thank you so much.
Thank you.
We have another question from the chat. Someone was wondering, did you calculate the photovoltaic coverage at warehouses, supermarkets, parking lots, and select businesses in your models?
We did not. We looked at density. So we didn't look at buildings, physical buildings. We just looked at population density and then and household data, and we assumed that. So I think we may have overestimated the capacity of households to integrate solar, because if they have a rooftop or not. But then we underestimated the capacity because we didn't consider these industrial or commercial customers. And that's something we are doing actually in the Duke Energy Initiative. There is an effort trying to use computer vision to create a very nice data set of both roofs and roof area and their relation with their orientation, their slope, etc., so that it allows calculating the potential for photovoltaic in the region. They also have some algorithms that identify when they take aerial images, they can identify if a rooftop has or doesn't have photovoltaics already, which is something we don't have.
Great. Well, I think we're at time. We really appreciate your presentation, and thank you everyone for joining.
Thank you very much, everyone. Thank you, Rachel and Kevin. It was great to see you.
Yeah, thank you, Dalia, for your presentation. And I really learned a lot. So, all right, see you at the next talk.